Welcome to Gallus Coder. Today we have another Zig programming episode where we will program Zig to generate Game Genie codes. Or as we belovedly call it, the GeeGee. Motherfucker! So the Game Genie, or the GeeGee as it was belovedly called, was created in 1990 by an English company. And basically their slogan was, it will make games last longer.
It can make games last longer.
Well, so does Viagra. But this looks more like a contraption you find in some BDSM dungeon. Or worse. Da sind sie wieder, Herr Coder. So where were we again? Oh yes. This will hurt you a lot more than it will hurt me. Bring in the GeeGee. Go? You said, Herr Coder? At least let me first look it up for you. After all, we're civilized people, not some animal. What was that? Go fuck me? Yes, I will fuck you with my GeeGee after I've looked it up, Herr Coder. What is it with you, Dutch? You're always so impatient. Always in such a rush. It really reflects poorly on your already worthless culture. Oh boy. Then I'd rather stick it in my old box. So the Game Genie, or belovedly known as the GeeGee, actually sat in between the CPU and the ROM cartridge. And those magical codes that either consist out of 6 characters or 8 characters contained an address and the data byte to change on that address, and if you had that 8 character code, also a compare character. So it would actually compare that, for example, on address 8000 we expect FF to be there and change that into 80, something like that. And yeah, these codes are really only generated by a lot of bitwise operations, and I want to use Zig to later on program embedded devices, and I do a lot of bitwise operations on these embedded devices. So I figured, what can we do to actually have something to show and make a funny video out of it that also does these bitwise operations so I can learn them as well. Well, that was generating codes for the Game Genie. So we will pass in the address, the byte that we want to put on that address, and an optional compare byte. So basically we're going to write code to generate codes to change code. Oh boy, this is going to get very confusing very fast. Let's jump in. So if you are on Zig version 11, which I'm currently not, and this was also the reason why in the previous video that that this didn't work. And then you can capture the eye, etc. This still only does while loops. And we're going to use the while loop now as well. And we have to actually. But if you have Zig 0.11, and I urge you, just install that. That's so much better. You also have the Zig in it, and you can just do this, and it will create this project folder, NES_GG. It will create a source directory with a main.zig in it, with the whole boilerplate already in there, and a build.zig file. A build.zig file is basically just your make file. But since Homebrew is still on the old one, let's do it manually. NES GG. NES GG. I'm not going to make a zig.build file. That's too tiresome. encoder. And let's touch me on my main part. Touch my Ziggy. All right, okay. So let's open this up. I will be copying some code. Going to copy this. Here we import the sexual transmitted disease. Here we generate a general purpose allocator object. And there we return the allocator in the GPA, which we're going to use to get the arguments from the command line. And then we have the standard out that prints actually to standard out. And this one is very important in this case because this will do the heavy lifting. What we're going to do is we're going to create a program that's called NES GG, and it will accept a couple of arguments. So for example, an address and a byte value. Now what the Game Genie does, the GG, is it will look If address, in this case 8888, is called by the CPU, if so, it will disconnect the ROM, so it will do the chip enable, raise it probably, so not chip enable, raise it. So it's disengaged, and from the latch it will put this number there. And this is what is called the 6-character code, because when we're done, this will generate 6 characters. Now there's also an 8-character code, and that it comes from the fact that you can also have an optional compare byte, like this, for example. And what this does is, as soon as 888 is called, the Game Genie will check if that address contains this value, CE. If so, it will only set this data byte over there. If not, it will not change it. And the reason why this is very, very useful is, if you, for example, have Mario Bros, there were a couple of different versions. You had a Japanese version, an American version, a European version. And the byte that you want to change may not necessarily be on this address for all the 3 cartridges. So then it's very convenient to actually check if that value is there, what you expect, and not just blindly updating something and probably breaking it. So that's why we're going to have those arguments. So let me first start with the pop function main. This we know from the last video, bubble up the error all the way to the console. Right, void the main. We are actually going to catch errors in this video, because I think that is very, very useful, and I really like what Zig and Rust have done in that area. So let's get those arguments. This is new. Standard.process.args alloc and use the GPA. So what this does, it will generate a block of memory using the GPA that is big enough to hold all the arguments that we pass. In this case, we don't really need to actually delete it, but just do a defer just to be sure. Standard process. It's always good to clean up after yourself. If you get complacent, here we do it, there we don't, then you get confused. Always clear your memory. Free GPA, and of course we need to free that structure. So what this does, it says as soon as this goes out of scope, defers, then we call the args free function, and we use the GPA in this case, allocator, and that arg structure, so that will deallocate it properly. Okay, like we said, we can actually have 3 or 4 arguments. Of course, if you have NES, whatever, then you have 1, 2, 3 arguments, and if we have that extra compare, it's 1, 2, 3, 4. The name of the application is always your first argument value. So if args.len is less than 3 or args.len is larger than 4, then we have not called the program properly. So then we just give them a nice sensible message to tell them the usage is the program name, and we start with address. Then you have the data byte that you want to change, and optionally you have the compare byte that you want to change. And I always do this, always give an example, or in this case we're going to give 2 examples. So S0 X F12D DD, and this is, for example, 6 car code, and this is for instance the 8 car code. I always find it very important to write sensible user messages. I think they are more valuable than actual comments in your application. Well, let's use the same, and we expect F0 there. All right. And now we need to pass in a tuple where we replace this string, and this string. So we needed 3 values, args 0, args 0, and that is also arg 0. It's the same one after all, and there we go. And then we need to return because there is no reason to continue. Return. But if args.len equals 3, then we're actually going to try to call the GeeGee NES, which will be our lifting function that actually calls the encoder and calls the print functions. And we pass in the args1. Why did it move over there? Bugger. args1. args2, and of course we don't have the comparator in this case, so that is empty. And in this case we have the args3, the compare byte as well, and that of course needs to then become 4. All right. So let's create that GeeGee NES function. Let's make that public as well in case you want to expose it in a library, whatever. In that case, put this in a different file. We're going to get the address, and that is of an array constant U8. Then we get the data, which is of an array of constant U8s. And we have the compare, which is of an array of constants of type U8. A U8 is just an unsigned 8-bit value, which is the same as a character. Right, let's have a look what we need to do now. Yes, we first need a variable that can capture the encoded unsigned 32-bit value. And you always have to assign something in ZIG. If you don't know the value, then assign it as unsigned. And we need to check if it is an 8-character thing, a boolean, and we set that to false. And if comp.len is larger than 0, we set is 8 to true. Let me show you something else. I'm always changing the documentation during the video anyways. You can do this. Undefined. If it is larger than 0, then it's true. Else is 8 is false. It's sort of like a more verbose ternary statement. And we need a return value. We're not going to return anything. We're just returning void with bubble up the error in case we do not catch everything. Right, so let's keep it like this. Usually I do value here and then... but it's for learning purposes, right? So if not is 8. So then it's a 4-byte, a 6-character code. Then we need to actually say encoded will become the function from the function encode nest that we're going to call and make. And that will take in the adder, comma the data. And we can actually pass in the comp as well, since we make it 0, but I like to be explicit always. So in this case I say it's an empty one. Okay. Actually we can get an error here, and we're going to catch errors. So let's catch an error for the first time. So catch, and I want to have that error be caught in the variable error, that is the error tuple, and then you just create a closure, just like you do in Rust or JavaScript. And in this case we want to write a sensible message, try standard out, print, this was an error, and this is the error object, and input needs to be in range of 0x000 to FFFFF and 0x00 to FF. Technically, actually, hey, what? My spacebar is really starting to get naggy. Actually, this is more correct because the NES ROMs always start at 8000. Since we use the parseInt here to parse this, and we tell it it's a U16, it will find this appropriate as well. But since we're doing this, let's do that. Okay, and in that case, we need to still give the tuple with the error. And since we didn't put a type in here, it will infer this as the type for the error and just print a whole nice error. And we will return from this because there is no use to continue. Else, well, that is return. I type like a freaking toddler. There we go. Okay, that's the same, but we also have an extra one that can be in range of this. FF. And that should still work. All right. And in that case, then we have the encoded. Hey, I'm missing something. Boom. And boom. In that case, we have the encoded string, so we can then call a print function that we're going to create. So how are we going to call that? Let's see. Let's call it just print GeeGee NES, because in case you want to do something like Game Boy as well, then encoded. Yes, encoded, and we need that is8 there. And this can, of course, also fail. Let's make a nice little capture. There's a catch, error. This episode is about bitwise operations and catching errors. All right. And then try standard out, stout. Stout in Dutch means naughty. And I'm definitely a naughty boy. Print, error. And then give a sensible message underneath. Whilst trying to print GeeGee code. Probably never going to be called, but hey, better safe than sorry. And in that case, return because there's nothing useful to do. Okay, let's create that print function. Maybe we won't have that public, whatever. GeeGee, what do we call it? Print NES. GeeGee print GeeGee for the NES. All right. And we say we put in, what did we put in? We have the encoded, of course, which is a U32. And we have the is8, which is of type Boolean. All right. Now, the Game Genie, we have 8 nibbles here. And every nibble is transposed into a special character. It's not hexadecimal. So let's create an array which matches up with those characters. So we're going to say underscore. That will be replaced by the compiler by the number of characters that we're now going to immediately assign. U8. So if the value is 0, then it's an A. If the value is 1, it's a P. If the value is 2, it's a Z. All right. That should be the thingamajiggies. Oh, we need a return value, and that is void. Oh, we're not going to return anything from that. And now we come to the ugliest thing of Zig, that is loops. Still not happy about them. Because I was working on 0.11 and I figured, well, we have that for loop. It would make sense if I want a reverse loop from 7 to 0, that you do this. then it will realize, ah, well, we start at 7, we go to 0. No fucking way. It just doesn't work. So after about 20 minutes of fucking around, I was like, oh, we have to use that bloody while again. But yeah, that's good because we're filling this on 0.10 version anyway, so let's do that. So I do a U8 for I, and it is undefined because it's defined depending on what we're going to do. Let's use that same ternary statement. So if is 8, then I equals 7, because we from 0 to 7 is 8 characters, and else I is 5, because 0 to 5 is 6 characters. Alright, then we do the while. I greater or equal to 0, then I is I minus 1, and we do this. And this is another very dodgy, shitty thing from Zig, which I don't really like. I love Zig, but this is just crap. If you think, like, I'm going to break out when it's 0. Nope, it actually continues one more time, and it calls minus 1. And it's complaining then, the compiler, yeah, but this is an unsigned integer, you're going through 0. So you need to actually, in that case, this is really silly. And if somebody knows a better solution, please let me know. But this is what I came up with. And ironically, this is also what I found in documentation on Zig. But I just think it's wrong. Standard out, print the character. And the reason we're going backwards, I do that a lot, by the way, going backwards through structures like arrays. It makes sense to change them from the back to the front, because then you do not impact the rest of the array. And in this case, we're going from the least significant bit to the most significant bit. So hence we need to go backwards. So in our tuple, we're going to say from the characters array that we have, we're going to get the encoded value. We're going to shift that over the number of positions. And now we need to truncate. And this is another thing that I didn't understand, but the compiler warned me. I was like, I'm going to truncate this to a U4. And this is I. I'm going to truncate the U8 to a U4 because we're dealing with 4 bits. But the compiler said, yeah, but I expect a U5. I was like, okay, well, let's change to U5. But need to think about why that is. It didn't make any sense to me. Multiplied by the number of nibbles, so number of bits per nibble, 4, yeah. And then we still need to end it with 15, or F in this case. And then it should be correct. And then we still need to do one more print. Let's copy this, because we want a new line after we printed the characters. And that's just an empty tuple. All right. And I'm going to copy the code for the algorithm. That is just your bitwise operations. They are exactly the same as C. And that is the reason why I actually chose this little project for myself. You think I do these projects for you? No, I just document them. It's all selfish reasons. I just do it for myself. Because I was like, how do bitwise operations work in Zig? Because I use bitwise operations when I do embedded stuff, well, 99% of the time. It's just very useful. It's very little code. It compiles very small. It's really wickedly fast. So that's why I figured, what can I do in Zig that actually can make a nice little story, can show perhaps some retro stuff. Well, hence this thing, because I figured, yeah, I can remember that I needed to do a lot of shifting around of bits in there. And, well, this is just like how you do it in C. So we have the value of the data U16, which is parsed from our strings that we passed, right? The FE, for example. And we do an end on that, or in this case, in this one, end with 8. And then we OR it with that result, and we shift that over 12 positions to the right. And this, for example, G GG equals GG, shift over 4 positions, so multiply by 16. It's the same in all intents and purposes. It's identical to C, which was very good and very nice, because I really like not changing a lot of things. Zig build exe. Let's see what errors we have. Of course, there's always errors. 62, especially when I'm typing. STD out. Not stout. I'm naughty, I know. And of course, I copied that. Yeah. Copy and paste. Typical copy and paste errors. Did I actually... I need to have a proper... This is... if it's not 8... Yeah, so in this case we also need this one. Oh, we already have it twice. Sorry. I like the messages to be correct for the people. argslen dot filled. What did I do wrong here? argslen. Here we do the args. Oh, yeah. I need to put a try in front of there, because this can fail. So now, if it fails... Oh, did not want to do freeform. Get away. We're recording a video. I think this should work. Yeah, awesome. So let's run this. And let's check it against the online version. 08000, and I want to set it to FF. AVY, something definitely ran wrong. And I think it may have been, again, the order of the bytes. A, P, Z, L, G, I, T, Y. Yeah, definitely. Y. G, Y, E, O, X, U, K, S, V, N. Okay. But yeah, it seems to be working. Anyway, I'm still a bit wrong. NYAAE. I have one byte too many. 1, 2, 3, 4, 5, 6. I did something wrong in my count. That should be 5. That. Now it should work. Oh. NYAAE. Yeah. All right, and let's do a little test value there. CD. Let's add that as well. X CD. And something went wrong there as well. Why? Let's debug that for a second, real quick. I found it. Copy and paste error, of course. This needs to be CMP. And that is correct. NYE ask, yeah. Right. Copy and paste, always your worst enemy, right? But also your best friend. So for demonstration purposes, let's show what happens if we go overflow. We should get an error. Yeah, we get the error overflow. It's nicely printed, that object. And it says it needs to be in range of, yeah, that's absolutely correct. Right. And what happens if we do this? Yeah, that still registers it, because parseInt will actually say, that is 8,000, but then decimal. That is a tricky thing. Well, I figured let's implement this as well. So what I did is I created an isHex notation function. And what you do to actually compare slices, you can use the standard mem.eql equal. So if you want a whole slice, in this case, I only want to check the beginning. So it starts with 0x. And it returns true or false. And here, of course, I check for both cases that is valid, of course. And we need to check that args1 and args2 actually are hex. If not, we write address and data value needs to be a hexadecimal, start with 0x. And of course, you can still fudge up like so. Then here it even checks again. Okay, this last one is not in hexadecimal. It will actually alert you to that as well. So there you go. It's now even better. So there you have it. We created a nice little zig program that if you strip everything off, it's only 400 kilobytes to generate codes for the Game Genie. Now we have a lot of videos on this channel where we actually hack video games. And some of those one instruction hacks actually could work with a Game Genie. And there are several Game Genies for the NES, for the Game Boy, for the Sega, etc. And the cool thing is, back in the day, they came with these code books that already had the cheats in there. So you would just look up your favorite game. So Bad Dudes, for example. Nombre infini de free. That is probably number of infinite lives. Then you would just type in that code and that would give you that solution. And the funny thing is, these books came out on a subscription. So if you were really not a hacker like me and you needed these codes, you could just buy a book. And perhaps one or two of my own codes are actually converted into Game Genie codes in there, because I used to publish them a lot on these underground channels back in the day on the BBS. Yeah. And Zig, I am so impressed with Zig. That parseInt, it's brilliant. It does all the heavy lifting. I was initially going to actually write a conversion for hex to decimal, and then I figured, let's Google. Oh, parseInt already does that. That is really, really cool. So, yeah, Zig, you are awesome. Andrew Kelly and your team, fucking brilliant. Keep up the great work, and we will probably see some more videos. And probably also a video where we will hack a video game using the GeeGee. So I hope you learned something, and see you in the next one.